This video covers integral and derivative functions of time and the error bounds on them. This is part of the error analysis and data regression series. The motivation for this video is that many of the measurement instruments that we use for navigation require integration or differentiation to get the desired quantity from the measured quantity. For example, a rate gyro measures the rotation rate about a point, and often we want the position or the angle, and that requires integration of the rate gyro output. An accelerometer measures acceleration, but not velocity or position. To get those quantities, we have to either integrate once or integrate twice. An IMU has 3 accelerometers and 3 rate gyros together. So we're obviously going to have to do some processing to get orientation and position from those. A GPS measures position, but it's somewhat noisy. So if you want either velocity or acceleration, you're going to have to do some differentiation on that. Here we have the equation that we're going to use to model the output of a sensor. The output from the sensor, x sub m of t, is equal to the true output, x of t, plus some bias or offset, which we assume is a constant or DC amount, and some random noise, epsilon sub n of t, which we model as Gaussian white noise with a standard deviation sigma or s, depending on how we are modeling these things. The relationship in 1D between acceleration, velocity, and position, or angular acceleration, angular velocity, and orientation are shown below. The acceleration is the first derivative of the velocity or the second derivative of the position. The velocity is the integral of the acceleration or the first derivative of the position. The position is the integral of the velocity or the double integral of the acceleration. The angular quantities have the same relationship. The angular acceleration is the first derivative of the angular velocity or the second derivative of the angular position. The angular velocity is the integral of the angular acceleration or the first derivative of the orientation. The orientation is the integral of the angular velocity or the second integral of the angular acceleration. With these in mind, let's see what happens for real systems where we're actually sampling the data and not using continuous functions. Here we have acceleration, such as either from an accelerometer, or this could also be used for an angular accelerometer, which is a very rare device. The measured acceleration, time step t sub I, is going to be the true acceleration, time step t sub I, plus some bias, plus the random white noise at that time t sub I. To get the velocity from that, we will have to integrate the above equation, and when we do that, the integral of the true acceleration gives us the true velocity. The integral of the bias gives us a linear term in time, and the integral of the random white noise does not give us an actual function. It gives us bounds that we can observe. If we have the standard deviation and the sample time or sample period for this, we can discover that the observational bound is sigma times the square root of delta t times the square root of the time step that we're looking at. We will correct this later for confidence interval. The position, we're going to have to integrate the above expression again, and so the measured position is going to be the true position plus 1/2 of the bias times the step squared, and then 2/3 times the square root of the sample rate times the sigma of the white noise times time step sub I to the 3/2 power. Again, this is the observation bound. If we start with velocity instead, where we've got the measured velocity is the true velocity plus the bias and the white noise, we find the position is going to be the first integral of this. So again, we get the true position plus the bias times time plus the standard deviation of the white noise times the square root of time times the square root of the time step. The acceleration, on the other hand, since we're taking the derivatives, the derivative of a constant is 0, so we end up with the true acceleration plus some multiplying constant times the standard deviation. This multiplying constant is most easily calculated from the data and from your processing rather than trying to do a theoretical version of that. If we start with the position, again, we're going to have the same thing, the true position, the bias or offset, and the white noise. To get the velocity, we differentiate it once with respect to time, and so we end up with the true velocity plus some constant times the white noise with standard deviation as shown. If we take the second derivative, we end up with the true acceleration plus some constant that, again, we are going to have to determine from our actual processing rather than theoretical calculations, and then we have the standard deviation, which is going to be our noise again. We will look at these things further as we go through.